Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jin Kim, and today we're going to infinity and beyond. Specifically, we're going to talk about how some infinities are bigger than others, and how the heck that makes any sense. Let's get started. It's quite fun listening to kids talk because they can say some ridiculous things. Like when a kid says, "Dibs got times infinity," to authoritatively stamp down an argument with the biggest thing they can think of, infinity. Until someone says, "Well, did I dibs not times infinity plus 1? But is it bigger or more? Isn't infinity plus 1 just infinity? Infinity is one of those weird concepts. It literally means that something is not finite or limited in size or extent. In other words, infinity is endless, like the void in our hearts that no amount of chocolates or memes or other hedonistic pleasures can fill. So if something is endlessly big, then it must be the biggest thing, right? You can't count greater than infinity. Well, in today's episode, we're going to really wrinkle your brains because turns out there are things bigger than infinity. Even weirder yet, those things are other kinds of infinities. What? Surely you can't have more than one kind of infinity. Well, you can, and don't call me Shirley. For our ELI 5 this week, we're going to talk about one of my favorite thought experiments that highlights how strange infinity can be. Hilbert's paradox of the Grand Hotel. It's going to be a wild ride, but hang tight. We'll explain it all to you in detail throughout the episode. Let's go! David Hilbert was a mathematician who was studying the concept of infinity. In 1924, he came up with the following thought experiment to teach people more about how infinity works. Imagine a grand hotel that is so grand that it has an infinite number of rooms. The room numbers go 1, 2, 3, 4, past 100, past 1,000,000, and keeps going on and on and on endlessly, because that's infinity. Let's say it's peak season, and the infinite grand hotel is full of an infinite number of guests. Infinity rooms fits infinity guests. Easy, right? But then one more person comes to the hotel asking for a room. The manager, being quick-witted and trained in mathematics, solves this problem super easily by making an announcement to all of the existing guests. She tells everyone that they all need to move rooms. Specifically, each guest needs to move to the room that is their room number plus 1. So, if you were staying in room 1, you move to room 2. If you stayed in room 11, move to room 12, etc. Now, because there are an infinite number of rooms, everyone can shift one room and still make room for this new guest. Hooray! But what if 2 people came to visit the hotel? Well, then all you have to do is tell everyone to move to their room number plus 2. This works for any finite number, thanks to the hotel's infinite properties. But here's where it can get weird. Imagine a bus arrives to the hotel with an infinite number of guests, all wanting a place to stay for the night. How are you going to fit another infinite number of guests? You can't tell people to add infinity to their room number, because what would that number even be? So it's time for the manager to show off her math skills once more. Instead of adding a number to their room number, she tells guests to move to the room number that is double their current room number. So, room 1 moves to room 2, room 2 moves to room 4, room 3 moves to room 6, and so on. The keen-eared listener will know this means that every existing guest will move to an even-numbered room, freeing up the infinite number of odd-numbered rooms for the new guests. And that's how you fit an infinity within another infinity, with mad skills. Oh, what's that? This time an infinite number of buses, each with an infinite number of guests, all arrive at the same time. Whew, business is booming. But don't lose hope. The manager is prepared, because she knows that according to the ancient mathematician Euclid, there are an infinite number of prime numbers, numbers that can't be divided by any other number other than itself and 1. So, she can use prime numbers to generate enough room numbers to fit everyone in. First, she tells everyone already in the hotel to move to the room number that is 2 to the power of their room number. So, if you're in room 3, you have to move to room 2 to the power of 3, which is 8. Yeah, making your guests have to move every night and do maths along the way is not going to get you 5 stars, but at least you have an infinite amount of money pouring in thanks to the new guests. Anyway, once all of the guests have moved to rooms that are powers of 2, you can tackle the first bus of infinite guests. You tell these guests to note what their seat number is, because just like how the hotel has infinite room numbers, the bus will have infinite seat numbers to identify the guests by. You tell the guests of the first bus to go to the room number that is the next prime number, 3, to the power of their seat number, which means the first passenger goes to room 3, the second passenger goes to room 9, the third passenger goes to room 27, and so on. Thanks to the way prime numbers work, none of the powers of 3 line up with the powers of 2, so there'll be no room clashes. You can use this magic maths trick for all the other buses. You just have to move up one prime number per bus. So the second bus's passengers go to room numbers that are 5 to the power of their seat number, the next bus uses powers of 7, and the bus after that uses powers of 11. Eventually, you can fit in an infinite number of infinities in your infinite hotel. Bam! That's the power of infinity. Oh, is there no way to stump this amazing manager at this amazing hotel? Well, turns out there is, because not all infinities are the same. Enter the Infinity Party Bus. This bus is for partying, so there are no seats. So the only way you can tell the infinite guests apart is by their names. Except their names, too, are infinite. The partygoers all have very simple names. They're made up of only A's and B's. But there's an infinite chain of A's and B's in every order possible. So, guest 1 might just be called A, one called B, 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 one called A, B, A, B, A, B, A, B, A, B, A, and another one that's like ABBA, 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 ABBA. Every name is possible on the infinite party bus. Turns out, the manager is finally stumped because there's no possible way that she can house all of these guests. There's simply no way to match each person to a unique room. Why? Because up until now, all the infinities we've talked about are countable infinities, like 1, 2, 3 ad infinitum, or 2, 4, 6, or even the prime numbers, all discretely countable numbers that increase infinitely. But the names of the party bus guests are uncountably infinite, just like numbers like pi that have infinite non-repeating decimal places. And why does this cause a problem? Well, you'll have to stay tuned in until we talk about Cantor's diagonal argument and how this fits into the Grand Hotel. Or I guess doesn't fit in. Alright, hopefully by now you're used to entertaining the ridiculous scenarios of thought experiments. Thought experiments are useful because they let us visualize this complex concept and test it against different scenarios, to let us better understand it in a simple way. It's no surprise we like using them on Explain This. Hilbert's Grand Hotel, sometimes colloquially just known as the Infinity Hotel, is just this. We can take an impossible yet very simple concept, a hotel with an infinite number of rooms, and test how infinity works by gradually stressing it more and more. Through it, we've already covered things such as how there are countable and uncountable infinities, how the concept of full and size don't really apply to infinity, because you can just shift everyone one room over for extra room, and how you can have weird situations such as there being as many even numbers as there are whole numbers. Don't worry, we'll break it down all for you so that it's more digestible. Think of Hilbert's Hotel as a taster of what's to come. So, the simplest definition of infinity is something that is endless. When it comes to counting numbers, infinity suggests that you can keep counting upwards to no end. You can apply this to negative numbers as well. You can just get smaller and smaller and more negative to no end. Although we commonly think of 0 being the smallest thing, and infinity being the biggest thing, we can tell from Hilbert's Hotel that this isn't technically true. Not that infinity isn't big, but it's not quote-unquote the biggest thing, because size doesn't really matter for infinity. Ayo. For example, if infinity is the biggest thing, then what's infinity plus 1? Well, as we saw from Hilbert's Hotel, you can always add 1 to infinity to make it infinity again. You can even double infinity and it would still be infinity. So, already we can tell that infinity doesn't follow the same rules as a normal number, because it's not a number, it's a concept. To explain what infinity looks like, we need to learn some maths, which I hope isn't a surprise to you when you decided to hit play on an episode about a maths concept. But before we even start learning about set theory and cardinality, let's get some simple definitions out of the way, because if you're like me, God knows when you last took maths class. Alright, so there are a lot of different kinds of numbers in maths. The simplest are the numbers that we use to count with. 1, 2, 3, 4, and so on. These counting numbers are called natural numbers. Naturally. Natural numbers are a type of integer, which are whole numbers. You see, natural numbers are just the positive integers. Integers as a group also include 0 and all the negative integers, such as -1, -2, -3, and so forth. Cool. Hopefully you're with me so far, because now we start getting a little bit trickier with numbers that aren't quite whole. We have rational numbers, which are basically numbers that you can write as a fraction. So this would include all the integers, because you could write 2 as 2 over 1, or 4 over 2. But it also includes numbers like 0.5, which is 1 over 2, or 0.6 recurring, which is 2 over 3. Or even numbers that have weird patterns like 0.428571, 428571, etc., which is 3 over 7. So already, we have numbers that can have infinite number of decimal places. If there are rational numbers, then surely there are also irrational numbers. And of course, these are the numbers that you can't use any fraction to express, such as the square root of 2, pi, or the natural number e. These irrational numbers are even more complex than the rational numbers with infinite decimals, because there's seemingly no obvious pattern to the numbers that show up in the decimal places. And that's why there are pi competitions. No, not the ones where you eat an apple pie as fast as you can, but the kinds where people try to remember pi to the most number of decimal places, because it almost seems random. Anyway, all of the numbers we talked about up until now fit comfortably in a group called the real numbers, which sounds a bit like gatekeeping, and it kind of is. It includes almost all the numbers in existence, even the irrational ones. But there's still another type of numbers called imaginary numbers. And we're not talking about numbers such as bazillion or gajillion. We're talking about numbers that include the square root of -1, also noted as I. We won't go into them because imaginary numbers are a whole nother thing, but we'll mention them for completeness. Anyway, I promise we're getting to how infinity works. Alright, so there's a field of mathematics called set theory, where they study how sets work. Sets are super simple in their essence. It's basically just describing a group of things. So a set could be a bowl of fruits containing an apple, a banana, an orange, and a kiwi fruit. It could also be numbers. Like, we could define the number 1 as a set containing exactly one thing. The number 2 is a set with 2 things. And 0 is a set that is empty. It sounds weird to define a number, but honestly, maths needs a lot of strict definitions because otherwise it just all falls apart. Now, in set theory, the number of objects in a set is called cardinality, as in 1 is the cardinality of a set containing one thing. You dig? Try not to think of it too complexly. Just think cardinality is the number of things in a set. Alright, so now that we know the basics of sets and cardinality, let's tackle infinity. Infinity is essentially the cardinality of a set that just contains every natural number. 1, 420, 69, 42, all of the cool numbers as well as the boring ones. Simple, right? But how is this definition any different or more useful than our previous definition of something that is endless? Well, for one, it lets us study infinity better and understand how the manager at the Infinity Hotel did all those seemingly magic things. If we go back to finite sets, 2 sets with the same cardinalities can have their contents matched up 1 to 1. So for example, let's say we have a set of A, B, C, D and a set of 1, 2, 3, 4. Both sets have a cardinality of 4. This means you can match A to 1, B to 2, C to 3, and D to 4. Easy peasy. If the cardinalities don't match, then you can tell one set is bigger than the other. So for example, the alphabet has cardinality of 26, whereas a set of single-digit numbers only has a cardinality of 10. Ergo, we know that there are more alphabets than single-digit numbers, and there's no way to match the letters to the numbers without there being leftover letters. You can do this for any kind of sets. You can literally compare apples to oranges. So let's apply it to infinity. Let's take one infinite set, say a set of odd numbers. This set contains every odd number in the universe. We don't need to know what the humongous numbers that exist in them are because we've already defined the cardinality of the set as infinite. Now, let's take another infinite set and compare it to the odds. No, I don't know. Why don't we just take the even numbers? Both of these sets have the same cardinality, infinity, which means, you got it, you can match their contents 1 to 1 because the sets are equal size. You can match 1 to 2, 3 to 6, 5 to 10, and so on. We even have a simple rule for this. Just double each odd number to find its corresponding even number. This is exactly how the hotel manager fit an infinite number of new guests in an already full infinity hotel. She knew that by doubling every number, you create 2 infinite sets, even-numbered rooms that are filled with the old guests, and odd-numbered rooms that can accommodate the new guests. Now, here it gets weird, and how set theory helps explain why this weird thing works. Let's take 2 more infinite sets and compare them. A set with all the even numbers, and a set with all the natural numbers. So that's odd and even numbers. Simple logic will tell you that a set of natural numbers should have double the numbers compared to even numbers, right? Because you got even and odd. But in reality, both sets have a cardinality of infinity. As in, they're exactly the same kind of set. This is kind of Nani the flip moment you get with infinity maths. The reason why this works is because you're talking about infinity. We're no longer dealing with terms like size and as many. Like, you can't say, there are as many integers as there are even numbers. The concept just doesn't apply anymore. It'd be like saying you're turning the silence on, or that an average household has 2.19 children. The qualities don't really work for the context, unless you've got a bit of a child in your house, in which case the police might come asking some questions. And that's exactly why we need set theory, because instead of comparing sizes of sets, we can just compare the cardinality of sets. And in the case of even numbers and natural numbers, they have the same cardinality, infinity. Remember that cardinality doesn't necessarily mean size, even though in finite sets, it correlates with it. In reality, all cardinality is telling you is that you can pair up every object in 2 sets of equal cardinality, 1 to 1. In the case of the infinite hotel, this means that if a set containing a number of guests has the same infinity cardinality as the hotel's number of rooms, then you can house all of them. To make it easier to understand, let's go back to the infinity hotel and study the part where an infinite number of buses with infinite passengers arrive at the hotel. You can't just double or triple the room numbers to fit them, because you don't even know how many infinite people are there. And you know, because you can't use the words as many when it comes to infinity. So what the manager can do is make a grid. First, she takes the current hotel guests and puts them in the first row of the grid. So it would say hotel room, then H1, H2, H3, H4, and so on, infinitely. The second row is where we put the passengers of the first bus, but instead of room numbers to order them, we'll use seat numbers. So the person in the first seat of the first bus, we can label B1S1. This means that the second row will look like bus 1, then B1S1, B1S2, B1S3, and so on. If you do this with every bus, you'll end up with a grid. I'll put a picture up on the show notes so you can visualize it. So how can we match up a grid to a line of room numbers? Well, you can draw one really long line that is zigzagging diagonally through the grid. This line starts at H1, which is the top left corner. It moves to the right to H2, then diagonally back to B1S1. Then it goes down to B2S1, then it goes up and right to B1S2, H3, and so on. It's really hard to describe with just words, so please do look at the show note diagram. Anyway, the end result of all this zigzagging is that now you've converted a grid into a line. And if you're to stretch out this line into a straight line, then suddenly you'll have a list of all the hotel guests and bus passengers in a series. And all you have to do is put them into a room one by one. So H1 goes to room 1, H2 goes to room 2, B1S1 goes to room 3, etc. Hooray! You can even do crazy maths like taking the powers of each successive prime numbers to generate infinite rooms that fits the infinite number of buses of infinite passengers. All you need are 2 infinite sets of the same cardinality, and you can fit infinite people in the infinite hotel, one way or another. So, there are lots of different kinds of infinities, but weirdly, they can appear as a similar size because the concept of size doesn't really apply to infinity. Okay, but Jen, you told us that there are different kinds of infinities that aren't the same. If all infinities have the same cardinality, how can this be true? Well, this is where we introduce you to how there are different types of infinities. So far, we've only been talking about countable infinities. This means that if you had infinite time, you could theoretically count upwards from 1, 2, 3, all the way to, well, there's no end, but you can keep counting. The Infinity Hotel has a countably infinite number of rooms, and the buses had countably infinite number of passengers. Turns out that countable infinities are easier to work with than the next step of infinity, uncountably infinite sets. This is where the party bus example comes in. Let's recap. A party bus arrives to the Infinite Hotel. This bus doesn't have any seats, so you can't use countable seat numbers to allocate the passengers to their own hotel rooms. Instead, the only way you can identify each passenger is by using their name. Unfortunately, the passengers have infinitely long names made up of only A's and B's. Because their names are infinitely long, you have every possible sequence of A's and B's on the party bus. So the question is, can we fit these infinite passengers into the Infinity Hotel? We already know the answer to this from our thought experiment. No. But why is that? Aren't these passengers also just an infinite set, so the cardinality would just be infinity? Now here's where set theory becomes useful, because we can talk about why we can't house the party bus guests. This is because the set has a cardinality of infinity, but not the same kind of infinity. Instead of countably infinite, this set is uncountably infinite. What does that even mean? Well, we'll go into it right after a short break. And we're back. Alright, we finally get to this mysterious uncountable infinity. So infinite that not even Hilbert's Grand Hotel of infinite rooms can fit it. Some sets contain objects that just aren't countable. Let's take the most famous example, real numbers. As we learned already, real numbers include all numbers that aren't imaginary. Amongst these are numbers such as irrational numbers that can't be expressed as a fraction, because their decimal places seem almost like a random, non-repeating infinite sequence of numbers. Like pi is 3.141592653589793233846 and goes on forever. You can see there are no patterns to these numbers. Imagine that continuing infinitely long. You'd have literally every possible sequence of numbers in that one number alone. But if you take a set of all real numbers, you have an infinite number of these infinite numbers, much like our party bus. Consider that next time you use the phrase, all things considered. Have you really considered all the things? Anyway, the set of real numbers is indeed infinite, but in some ways, it is more infinite than the other infinite sets we've talked about, such as a set of natural numbers. We can show this experimentally too. A famous mathematician named George Cantor showed in 1891 exactly why the set of real numbers has a larger cardinality than natural numbers. Cantor used zeros and ones to illustrate his point, but we're going to use our party bus example and use A's and B's. So, take the infinite set that includes every name possible using A's and B's of infinite length. Next, make a list of all of these names. So, the first name might just be all A's, like A. The second name can be all B's, so B. Third name, let's make it easy and have A's and B's alternating, so A. The fourth name can be the same, but starting with B, so BA. We keep going down the list, having examples like ABBA, or truly random sounding ones like ABBA. Now that we have a list of all these names, we can now prove that this set is uncountably infinite, with the clever use of Cantor's diagonal argument. First, take the first letter of the first name and flip it. Since the first name is just A, the first letter becomes flipped and we have B. This will be the first letter of our new diagonal name. Why is it diagonal? Because the second letter will be the second letter of the second name on the list, flipped. Since the second name was all B's, this makes it A. So now the diagonal name has B-A. We continue down this diagonal, the third letter of the third name, the fourth letter of the fourth name, and so forth, except we flip the letter from A to B or B to A at each instance. Eventually, we get an infinitely long name that is guaranteed to be off by one letter from every name on the list, because we've taken one part of each name and flipped it to be wrong. This seems preposterous, right? How can an infinite list not have that name? It's literally infinite. It's got everything in there. And yet, Cantor's diagonal argument proves this to be true using logic. Very elegantly, in fact. Cantor used this argument, amongst many others, to prove that there are sets such as real numbers that are uncountably infinite. That is, you can always generate one object in the set that can't be paired one-to-one to a countably infinite set, such as natural numbers. And because of this, you can't fit the uncountably infinite passengers on the party bus in the countably infinite number of hotel rooms at the Infinity Hotel. If this doesn't make sense, let's give you one more example. Let's look at the real numbers again and try to count upwards. Obviously, we start with 0. But what comes next? Is it 1? It can't be. We have fractions and decimals that are between 0 and 1, like 0.5. Okay, so how about we follow 0 with 0.1? Again, we can find the number in between these two, like 0.01. And the logic continues ad infinitum, showing that you can't possibly count each discrete real number. There's just too many of them. So much so that it transcends beyond size, amount, or even countability. It's uncountable. Great, so we've proved that there are indeed sets that have a bigger cardinality than other infinite sets, such as the natural numbers. So how can we note this down? We can't call their cardinality infinity as well, because then we'll confuse it with the countable infinities. And of course, mathematicians love defining things, so they came up with a system. First, they take the countable infinite sets, such as natural numbers, and they arbitrarily say that the cardinality of these sets are Beth null, or Beth 0. Beth being a Hebrew letter, because mathematicians used up all the other cool Greek and alphabetical letters in other places such as physics. Next, they take the uncountable infinite sets and call their cardinality as Beth 1. This way, you can easily show that sets with cardinality Beth 1 are greater than those with cardinality Beth 0, much like how a set of cardinality 2 is bigger than that of cardinality 1. 2 is greater than 1. Beth 1 is greater than Beth 0. And because cardinality Beth 1 is more than Beth 0, we know that there's no way to match all the objects between these two sets one by one. And that's why we can't fit the party bus passengers in the Infinity Hotel. When you delve deeper into infinity, it gets even weirder. Like, you'd think Beth 1 must be the biggest infinity, but in fact there are higher order infinities such as Beth 2, or even Beth Omega, which kind of sounds like a naming scheme in shonen manga like Dragon Ball or One Piece, but that's how it works in maths. There's always a bigger fish, or a fish with higher cardinality. You can even do weird things like doing arithmetics using the Beth numbers, like how if you add Beth 0 plus 1, you still get Beth 0, because a countable infinity plus 1 is a countable infinity. But if we delved any deeper into the world of infinity mathematics, your mind will probably explode, so let's stop there and descend back to our mortal plane of maths that we're more familiar with. We'll take a short break, and we'll talk a little bit more about infinity in different ways that don't involve sets and cardinality. Like, where did the infinity symbol come from? What's the philosophy of infinity? Why were ancient Greeks afraid of infinity? All this and more after the break. Welcome back. So, even though the mathematics around infinity only got more defined in the past 200 years, people have always thought about the concept of infinity. Like, it doesn't take maths to imagine a bottomless hole that never ends, or thinking about eternity. Such as, what happens in the afterlife? What happens if you let a thought experiment balloon out of control until there's no bounds? Human beings have always been testing the limits of our imagination and restrictions, and infinity is the ultimate test, because there are no bounds. We see examples of this all around the world, like in Hindu mythology. One of the epithets for Vishnu is Ananta, which became a term for something with a beginning but no end. There's also the Ouroboros, an ancient symbol found all the way back to ancient Egypt that shows a serpent eating its own tail in the shape of a ring. This symbolized the cycle of life, death, and rebirth, like a snake eating itself to grow longer ad infinitum. It probably came from the motif of snakes molting from their own skin, and we see this kind of symbolism all around the world, like in Norse mythology and South American indigenous people. When we come to the ancient Greeks, the progenitors of Western civilization, we see people thinking about infinity then as well. Zeno of Elea is a particularly famous Greek who toyed with the concept of infinity, such as the paradox of Achilles and the tortoise. Imagine that Achilles and a tortoise were involved in a foot race. Achilles, being proud of his strength and speed, gives the tortoise a head start of 100 meters. Once the tortoise crawls 100 meters, Achilles starts dashing forwards and quickly catches up in 10 seconds. But in the 10 seconds, the tortoise had slowly and steadily crawled forwards another 10 meters. But no fear, Achilles can catch up that distance in only 1 second. But then the tortoise has crawled forward another meter. No matter how fast Achilles is, because he takes time to catch up to the tortoise always advances a fraction further. So does this paradox mean that motion is impossible and Achilles can never outrun the tortoise? Well, no, and we'll show you why in a second. But these kind of paradoxes highlight a fascinating aspect of human history, the horror of the infinite. There's many suggestions from records that the Greeks were uncomfortable with the concept of infinity. For example, the Greek word for infinity is apeiron, or unbounded, and it's considered one of the materials the primal chaos was composed of. You can also see from stories such as Sisyphus endlessly pushing a boulder up a hill only to watch it roll down the other side, Tantalus, who is forever thirsty and hungry but can never reach the fruits or pool of water around him, and Prometheus, of course, who has his liver picked up by an eagle for eternity, that infinity and eternity seem like an awful punishment. Even Aristotle suggested that actual infinity must be impossible because of the contradictions and paradoxes. And it's not pure silliness to be afraid of infinity. Consider how people go mad in H.P. Lovecraft's works when they realize how infinitesimally tiny we are in the grand scheme of the universe, or the exploration of how maddening true eternity would be in works such as Stephen King's short story The Jaunt, or the Black Mirror episodes dealing with digital replicas of personas. True cosmic horror. Anyway, it seems that the horror of the infinite didn't stop clever people thinking about infinity, or studying it. Pythagoras and his followers thought the universe must be full of infinite numbers. And that's true, as we've learned from set theory. So, before I forget, how can Achilles overcome the paradox and beat the tortoise? Well, it's simple maths. The paradox is only considering the trees and not the forest. Specifically, this paradox is just describing a simple geometric series. Achilles needs to run 100 meters, then 10 meters, then 1 meter, then 0.1 meter, ad infinitum. If we show this mathematically, then it's 100 plus 10 plus 1 plus 0.1 ... to infinity. But we have maths that can show what a geometric series adds up to. In the case of the above formula, the answer is 111.1 recurring. So if we say that Achilles can run 100 meters in 10 seconds, then it should only take him 11.1 recurring seconds to complete this distance. Which again means that after 11.2 seconds, Achilles transcends the infinite geometric series, overtaking the tortoise and winning the race handily. Geometric series are interesting examples of how a finite thing can be split up infinitely small, and it's quite useful in the field of mathematics and economics. Like we've already talked about compound interest and mortgages and investments in episode 4. Anyway, let's move on from the ancient Greeks. As we move into the Middle Ages, people are becoming more comfortable with the idea of studying infinity. In 1638, Galileo discusses his famous Galileo's paradox. You can divide integers into two groups, those that are square numbers like 4, 9, 16, and those that are not. Therefore, there must be more integers than square numbers. And yet, every number only has one square number, so there must be an equal number of integers and square numbers. How can this be? We, living in 2023, having listened to Jens explain this, already know all about set theories and cardinalities and countably infinite sets, so we can scoff at the paradox all hoity-toity. But still, it's fun to see that this is one of the earliest mentions of the concept of matching 1-to-1 between two countably infinite sets. In 1655, mathematician John Wallis was the first to use what we call the infinity symbol. I'm sure you've seen the symbol before. It looks like an ape that got lazy and is taking a nap on its side. In branding, it's actually called a lazy ape. It symbolizes infinity because you loop around and around ad infinitum. It's an elegant and useful symbol that we still use in mathematics to denote infinity, as well as on things such as cameras to denote a focal length set to infinite distance, or to denote a type of long-lasting acid-free paper in bookbinding. And here's a fun fact for you. The symbol has a name. Of course it does. It's called a lemniscate. There, you can impress all your friends at your next party with your excellent maths knowledge. Infinity explodes in popularity from here on out, with Isaac Newton and Gottfried Leibniz using infinity extensively in calculus, recognizing that there are many infinite series in maths, such as the exponential series that tend toward infinity. I won't go into all the developments about infinity, but I will mention one last thing: the Mobius strip. The Mobius strip is a super simple, yet weirdly cool structure that was discovered in 1858 by August Ferdinand Mobius and Johann Benedict Listing. You've probably seen or even made it at some point in school. Basically, it's a flat ribbon that has been twisted once, then had the ends joined up. But the cool thing about this special strip is that if you were to put an ant on one surface and make it walk along the ribbon, it will end up walking on both sides of the ribbon eventually. There's also no way to orient it because you can't tell if the strip is turning clockwise or counterclockwise. It's a true symbol of infinity. The funny thing is, even though it was formally discovered in 1858, we see examples of it in both designs, such as Viking motifs and Roman mosaics, but also in mechanical systems from the 1200s, where engineers suggested twisting a conveyor chain once and joining it up to form a Mobius strip. This is a technique that we use to this day, something called the Mobius drive, which lets a conveyor belt use both sides of the belt, making it last twice as long. It also prevents it from twisting up. Anyway, you see the Mobius strip in all sorts of applications, such as roller coasters, world maps that can have their antipodes or opposing poles show opposite each other, and even on every can in the form of the recycling symbol. Some people even think it's where the lemniscate or infinity symbol comes from, but we already know that the symbol came first. Anyway, that's a lot of musings about the history of our relationship with infinity. Let's talk a little bit more about how ridiculous infinity can get in philosophy and thought experiments, and end the show there. Okay, so it turns out when you don't have boundaries, things get weird. Good interpersonal relationship advice as well. For example, consider the infinite monkey theorem. Imagine the Infinity Hotel again, but this time, every room has one monkey and a typewriter. If every monkey in the hotel were to randomly hit keys on the typewriter one by one, for an infinite amount of time, then you're guaranteed that at some point, any possible text will be typed. Whether it be the full lyrics to Veracastly's Never Gonna Give You Up, or Shakespeare's Macbeth, in the scope of infinite time and infinite monkeys with typewriters, the most complex, unlikely things can happen. This is because if there is even an iota of possibility that something could happen, in the scope of infinity, anything can happen, because there's no end. To highlight just how long an infinite time can be, consider this quote by Hendrik Willem van Loon. High in the north in a land called Svefjord, there is a mountain. It's 100 miles long and 100 miles high, and once every 1,000 years, a little bird comes to this mountain to sharpen its beak. When the mountain has thus been worn away, a single day of eternity will have passed. Our finite minds can't really comprehend the sheer magnitude of infinite space and infinite time, because it transcends size. That's why we have maths and science and logic to extrapolate things, because we can't visualize it. Like, we can't picture a hotel with infinite guests, but we can use maths and logic to figure out how to put more people in it, even when it seems full. And studying infinity helps us understand how our brains handle statistics. Like, people frequently mock the theory of evolution, claiming that it would be as if a junkyard assembled itself into a plane. But when you have ample time, say millions and billions of years, those kind of things are possible, where complexity can build and refine itself through time and random chance. Just because we can't understand it, doesn't mean it doesn't exist. We've already considered how awful an eternity might be to live out, from the examples of Sisyphus, Tantalus, and Prometheus. We even discussed in our first episode about Schrodinger's cat and the possibility of quantum suicide. But perhaps my personal favorite philosophical consideration of infinity is from John Green's book, The Fault in Our Stars. Without spoiling the story, because I think it's a delightful book and everyone should read it, one of the key themes of the book is that there are different types of infinities. As the character Hazel describes it, there are infinite numbers between 0 and 1, and there are infinite numbers between 0 and 2. Although the range between 0 and 1 seems to be smaller than 0 to 2, it still contains an infinity nonetheless. And thanks to set theory and cardinality, we actually know that this infinity is no smaller or lesser than the infinity between 0 and 2. It's just a different infinity. So even if a person's life may seem unjustly cut short, whether it be through terminal illnesses or world events, every life has the potential to be anything and everything that person wants, because they're each an infinite set in their own right. I think it's a beautiful metaphor because it takes a mathematical principle that you can't apply concepts like size and amount to some things like infinity, and take it to show that you can't gauge a life by any measurable quantity. Life is what the person living it defines it as, It's an uncountable infinity. And if there's one thing we've learned today, it's just how mysterious and wonderful and enigmatic uncountable infinities are. So stop trying to compare your infinity to other infinities, especially on social media. At the end of the day, we all share lives with the same cardinality, and you can make your infinity as pretty and exciting and content as you want it to, because it's your infinity. And if none of that makes sense, that's okay too. You've got an infinity to figure out, kind of. Well, to avoid this episode lasting an infinite amount of time, let's call it a show there. So, what did we learn today? We learned about what infinity is, or at least how it's defined by cardinality and set theory. We learned that there are countable infinities and uncountable infinities, and how they're different enough that you can't apply the same rules to them. We learned that you can't use terms like size and amount to infinity, because it transcends that. So an infinity that seems like it should be bigger than another infinity really isn't. We learned about some interesting thought experiments, such as Hilbert's Grand Hotel paradox, Zeno's Achilles and tortoise, and the infinite monkey theorem. Lastly, we learned a lot of maths, but also how it might be relevant to our lives through the power of metaphors. Alright, for today's 2-minute explain, let's talk about a famous math problem. What happens when you try to divide a number by 0? If there's one thing you should remember from maths, it's that one should never divide by 0. It'll break the universe. I mean, not really, but it will do some weird things. Division is basically splitting up a group into smaller groups. Like, if you want to split up 10 cookies amongst 5 friends, the answer is 10 divided by 5, which is 2. So, if you want to split a group into 0 or nothing, then that should mean infinity, right? Because you can do it over and over without a result? Well, no, for many reasons. The simplest reason is that it just doesn't make sense, even at an elementary level. You can't distribute 10 cookies amongst 0 friends, because you've got a friend in me. Sorry, back to serious maths. It's because the sentence makes no sense, distributing to no people. And maths supports this. Let's see what happens when you try to divide a number by smaller and smaller numbers approaching 0. 10 divided by 1 is 10. 10 divided by 0.1 is 100. 10 divided by 0.01 is 1,000. And 10 divided by 0.001 is 10,000. You can see that as we divide by a smaller number, the result grows humongously, exponentially even. So this must mean that as the smaller number approaches 0, we should be tending towards infinity. Which is true, but the problem is this curve on the graph will keep climbing sky high towards infinity, but it will never actually cross to that 0 point. Okay, so the calculus-savvy listener might say, well, can't you say that a function of x divided by 0 tends towards infinity? QED? Ha ha ha. Again, no, because maths won't let you have fun like that. Because consider the opposite of this. If you divide a number by smaller and smaller negative numbers, what happens? 10 divided by negative 1 is minus 10. 10 divided by negative 0.1 is negative 100. 10 divided by minus 0.01 is minus 1000. As you divide by a small negative number, the result becomes increasingly negative. Which means as you approach 0, this function tends towards negative infinity. How could that be? You can't have 10 divided by 0 be both infinity and negative infinity. And this is why we say that the answer to the question 1 divided by 0 is undefined or indeterminate. There is no answer. But you know what? Math seems to define things arbitrarily all the time. Let's skip over all the technicalities and just say that 1 over 0 is infinity. What happens now, smart guy? Well, you break arithmetics, that's what. In maths, there's a simple principle called the multiplicative inverse. Oh, that's a word to say. It's a fancy way of saying that if you take a number, let's say 2, and flip it so that you get 1 over 2, you have its multiplicative inverse. This is because 2 times 3 is 6. Then if you times 6 by 2's multiplicative inverse, 1 over 2, you get 3 again, because it's a half. And a number multiplied by its own multiplicative inverse is always 1. Like 2 times a half is 1. So this means that 0 times its multiplicative inverse, 1 over 0, must be 1. We just forced 1 over 0 to be infinity, so now we have the equation 0 times infinity is 1. Huh? But that must be wrong. Anything times 0 is 0. And if you ignore this fact, now you break arithmetics. Because if 0 times infinity is 1, then 0 times infinity plus 0 times infinity must be 1 plus 1 equals 2. But if you use some simple algebra, you can rearrange that equation to be bracket 0 plus 0, close bracket, times infinity equals 2. And since 0 plus 0 is 0, you've just made 0 times infinity equals 2. But since we defined 0 times infinity equals 1 just before, we've just proven somehow that 1 equals 2, which means that 1 plus 1 equals 3. All of this just doesn't work because 0 is such a special number, and infinity isn't really a number, it's a concept or an idea. So it's not really that you shouldn't divide by 0, it's more that you can't divide by 0. It's a meaningless, answerless maths problem. And if you try to force a machine like a calculator or computer to do it, it'll either spit out an error because the answer approaches infinity, or because it's been told specifically not to divide by 0, like you, or it will try to calculate infinity and the program will crash, much like when programs try to run infinite loops. So, there you go. The power of infinity strikes again. Well, that's it for today. Thank you for listening to Explain This. Hope you learned something interesting and maybe even useful today. We'll see you next time. Bye for now. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter.